Good afternoon, everyone. My name is Maaneli Derakhshani. I'm a postdoctoral researcher in theoretical physics at Rutgers University in the Department of Mathematics. And in this talk, I want to do a comparison between the proposal of ENSO warming, that is warming from the El Nino Southern Oscillation, as compared to warming from the greenhouse effect of carbon dioxide. And this is a follow-up to an earlier presentation I did for the Tom Nelson podcast entitled, Does ENSO Dominate Global Warming? In which I argued that ENSO warming plausibly explains most of the global warming observed over the past half century via satellites and weather balloons and other temperature data sets. But in that presentation, I ignored a comparison of CO2 warming to ENSO warming. Yet we know that CO2 does impart radiative forcing and hence could be warming the atmosphere alongside or along with ENSO warming. And I say could be for reasons that will become clear later on. And this recognition that CO2 is a greenhouse gas raises some questions which I want to address as part of the objectives of this talk. So first question is, what is the place of CO2 warming relative to ENSO warming? How does the magnitude of CO2 warming compare? Second question is, how does the magnitude of CO2 warming compare to the magnitude of ENSO warming? And does evidence for ENSO warming give insight into the magnitude of CO2 warming? And finally, how might CO2 warming impact ENSO warming? So before addressing these issues, I want to recap the evidence for the dominance of ENSO warming in the past half century from the previous presentation I gave. So the first piece of evidence I gave was this chart comparing, juxtaposing the UAH satellite-based temperature anomaly data set from 1979 to 2023 with the multivariate ENSO index version 2 from NOAA. And what I noted is that there are clear visual correlations between El Nino events, such as this one, and a few months earlier than spikes in the temperature anomaly of the satellite data, and then dips in the satellite data following a La Nina event. And likewise with these El Ninos, and then spikes, and then dips from the La Ninas, and so on. This corresponds to this, and so on and so forth. With, of course, the exception that at certain periods, like this one here, where this massive El Nino didn't produce that much warming, or where this series of El Ninos corresponding to a dip in the temperature graph, this is where major volcanic events occurred. Around here, Mount Pinatubo, whereas here, El Chican occurred and presumably induced ad hoc cooling, which depressed or just completely reversed the warming impact of ENSOs. But apart from that, there are clear visual correlations between variations in the multivariate ENSO index version 2 and the changes in the temperature anomaly data sets. The second piece of evidence I presented was the correlation between the Southern Oscillation Index and the variations in the temperature anomaly measured in the lower troposphere by the UAH satellites. And in this study, it was shown that the Southern Oscillation Index, 7 months lagged, accounts for 72% of the monthly variance in the global satellite record of UAH, 68% of the variance in the Rat Pack weather balloon data set, which I presented on the next slide, except for periods where, of course, volcanoes occur, which are removed in calculating the correlation. And 81% in the tropics, and we'll see that chart later on in the presentation. Third piece of evidence was this Analysis of Global Warming in the 21st Century by Dr. Roy Spencer, who noted that the multivariate ENSO index from the year 2000 to 2018 had an upward trend entirely because of this big El Nino event. He addressed the question of what happens if you remove this El Nino event in terms of how it impacts the temperature anomaly trend per decade of the UAH satellites, which he analyzes regularly, and also of other temperature data sets like HAD-CRUT. And he found that when you restrict the time period from 2000 to mid-2015, the MEI has no trend. That's what the dashed line shows. And the satellite data set of UAH has a trend of 0.01 degrees Celsius per decade. So virtually all of the warming is accounted for. And even a big chunk of HAD-CRUT's warming is accounted for as well. And the final bit of data of evidence that I presented was this report from 2016 due to Wallace, Christy, and DeLeo, which asked whether adjusting temperature time series only for the impacts of ENSO via the multivariate ENSO index, the cumulative MEI, and the 1977 Pacific Shift MEI variable can account for all of the positive and statistically significant warming trend. And their answer to this via standard econometric modeling, that is regression analysis, for 13 different temperature time series was that, yes, it can. Just adjusting for these MEI-related variables is sufficient to account for all of the temperature trend in all of these time series. And just to give a quick review of what the MEI metric was that they use annual average MEI, which dates back to 1949, and the cumulative version thereof. And as you can see, from 1959 to 1976, there was a net negative impact due to the preponderance of La Niñas over El Niños. And from 1976 to 1998, a net positive impact due to the preponderance of El Niños over La Niñas. And then they essentially balance out from 1998 to 2015. And here is the global satellite data sets average of UAH and RSS versus their MEI-based model fits. The model fit is the red line. The data is the blue line. And as you can see, the model fit is perfect. And when you adjust the trend in the temperature data set or changes in MEI, the trend is completely flat. Similarly, for the HAD-CRUT surface temperature data set, the model fit is extremely good to the Hadley gas to the global anomaly surface temperature data set. And when you adjust for changes in MEI, the trend is flat again. Okay, good. So now coming to the question of CO2 warming, I want to first ask or address the question of how big is the direct greenhouse warming effect from atmospheric CO2 alone? So there's a very nice review paper by Weingarten and Happer, which summarizes their work involving detailed calculations of the effects of greenhouse gases, and which they show that a doubling of atmospheric CO2 reduces the thermal radiation flux to space by about 1% in a model of the atmosphere which is transparent with no clouds and no other greenhouse gases. And this produces a radiative forcing of about 3 watts per square meter, a very tiny effect. And to first approximation, this increases the surface absolute temperature by about 0.25%, which corresponds to a temperature increase of 0.75 Celsius. A very tiny effect. So for example, since pre-industrial CO2 concentration in the atmosphere was about 280 parts per million. According to this, a doubling of atmospheric CO2 concentration to 560 ppm would increase the absolute surface temperature by only about 0.75 Celsius. And by the way, we're currently at 420 parts per million. This chart shows how the flux to space, the radiation flux to space, is inhibited from the case of no greenhouse gases at all and a completely transparent atmosphere. That's the blue line, the Planck blackbody spectrum, as compared to the case of greenhouse gases like water vapor and nitrous oxide, methane, which is the green line, the jagged green line, and no CO2. CO2 is 0 ppm. And then the change in this profile when there's an increase of CO2 from 0 ppm to 50 ppm. So that first increase yields a bite in this graph that corresponds to this light blue line. But then subsequent increases or doublings of CO2 increase that bite in the graph only very, very minorly. And it requires a doubling of CO2 each time in order to produce further dips in this graph. So this effect where CO2 has to be continuously doubled to produce the same radiative forcing or increase in the temperature is reflective of the fact that the temperature increase of the planet due to the radiative forcing from CO2 is logarithmic in the concentration, the atmospheric CO2 concentration. This ratio where CFT is concentration time at some time greater than 0 relative to the concentration at T equals 0. And S is the notorious climate sensitivity parameter, which is the subject of great debates. So this is what's meant by the saturation effect of warming, of greenhouse warming from CO2. It's much harder to create the same amount of warming for a given concentration of CO2. So we can show that the direct warming from CO2 is in fact too small to account for the warming that's been observed by satellite records, for example. So if we take the UAH global trend in the lower troposphere from 1979 to 2023 of just 0.13 Celsius per decade, we can estimate that the actual warming since January 1979 has been about 0.75 Celsius. On the other hand, given that atmospheric CO2 concentration since 1979 has increased by only about 82 parts per million, we can estimate that CO2 direct warming since 1979 must have been only about 0.18 Celsius. So the actual warming is about 3 times greater than what we would get just from direct warming from the CO2 greenhouse effect. So clearly far too small. So then how does the IPCC, for example, get a best estimate of 3 degrees Celsius increase from pre-industrial levels by like 2100? Well, to get this best estimate, they assume, as do proponents generally of anthropogenic warming, that water vapor and clouds provide net positive feedbacks to amplify warming from CO2. And they put this assumption into climate computer models like the so-called CMIP models that IPCC relies on. And the basic idea for them is that the direct warming from CO2 will increase the temperature of the atmosphere, which means there's more evaporation of water from the surface, which occurs, and thus the atmosphere holds more water vapor, which is the most abundant greenhouse gas and hence more powerful as a greenhouse gas than carbon dioxide. And the more atmospheric water vapor there is, the more warming occurs as a result. And the more CO2 that's put into the atmosphere, whether by humans or natural causes, the more water vapor it can retain, the more warming there is, and so on and so forth. So the anthropogenic warmists, like IPCC, estimate this water vapor feedback mechanism using something called the Clausius-Clapeyron relation from thermodynamics, which says that the atmosphere holds 7% more water vapor per degree of Celsius increase in the surface temperature. And this relation is well established in laboratory experiments. But the question is, does it actually hold for the climate system? And that's not clear because the climate system includes many other variables, one of which is clouds. And we know that some clouds, like thick low clouds and so-called warm clouds, strongly reflect sunlight back into space while having little impact on infrared radiation escaping to space. So they are opaque to sunlight, but essentially transparent to infrared radiation. And as a result, such clouds produce a significant negative feedback to CO2 warming. We've all experienced this ourselves on a hot summer day, for example, standing underneath the sun, feeling the warmth of the sun beating down on us. But then when one of these clouds passes over where the sun is in the sky and blocks that sunlight, it gets noticeably cooler in that region. And that's an instance of the negative feedback effect from certain types of clouds. We can experience it directly, and that's how strong of an effect it is. On the other hand, there are other kinds of clouds like upper level thin cirrus clouds that let sunlight through, but are very effective at preventing heat from escaping into space. They essentially block IR radiation from going into space. And they produce a positive feedback to warming. However, there is an exception to this, a proviso, which is the so-called iris effect identified by Richard Lindzen and his collaborators. And it's a bit complicated to explain, but for certain reasons having to do with complicated cloud microphysics and atmospheric circulation dynamics, such cloud coverage, that is upper level thin cirrus clouds, the coverage of the atmosphere in the tropics reduces in response to warming of the atmosphere there, which has been confirmed by satellites. And this reduction in such cloud coverage implies a negative feedback, because if there's a reduction in such clouds in the upper level of the atmosphere there, then that means that more heat can escape to space there, which is a kind of cooling mechanism. So clouds are a complication in the climate system that means that it's not so straightforward whether water vapor implies entirely a net positive feedback to CO2 warming. And in fact, the IPCC's AR6 report concedes that clouds remain the largest contribution to overall uncertainty in climate feedbacks in climate models, and they assign a high confidence to this statement. And interestingly enough, at any time, about 2/3 of the Earth's surface is covered by clouds. That's exemplified in this blue marble photograph from Apollo astronauts, where the marbling is the white stuff here, which is cloud coverage. It's quite substantial. So as far as anybody knows, the net feedbacks from clouds and water vapor could be significantly negative and could cancel out most or all of the warming from CO2. But there's a great deal of uncertainty here. And as an example of this, in a work by physicist Patrick Frank, who analyzed these general circulation climate computer models by essentially working out the propagation of error associated with modeling global annual average cloud coverage fraction within CMIP5 climate models. He notes that the annual average error is plus or minus 12% in modeling global annual average cloud fraction. And this error is widespread across such computer models. And the resulting error introduced in the long wave cloud forcing is an annual average of plus or minus 4 watts per square meter. So in other words, there's an uncertainty here in the simulated tropospheric thermal energy flux which is 114 times larger than the annual average change in tropospheric thermal energy flux produced by increasing greenhouse gas forcing since 1979. So in other words, the increase in radiative forcing due to the rise in greenhouse gases since 1979 is 114 times smaller than the uncertainty associated with annual average cloud coverage. So one cannot even infer from any of these climate models that a projected rise in global average temperature is due to greenhouse gas forcing as opposed to changes in global annual average cloud fraction. That is a fraction of the surface of the Earth that's covered by clouds and the feedbacks associated with them. They could be either highly positive, net positive, or highly net negative. And interestingly enough, NOAA's own International Satellite Cloud Climatology Project concedes the very same thing. Though I'll briefly note, they say that today's climate models must be improved by about 100-fold in accuracy in order to accurately make the statement, to accurately infer that a change in radiative balance at the surface of 2% will yield a warming of 2 to 5 Celsius or so. So even they admit that climate models, the CMIP models, are extremely far off from being able to, from being used to make such an inference. Nonetheless, despite this uncertainty, there are specific predictions that can be made by the assumption of net positive feedbacks amplifying CO2 warming. One of which is the so-called hotspot in the tropics, the tropical region of the lower atmosphere, the lower troposphere. So the tropics is this purple band around the globe. And the tropical upper troposphere is about 30 to 40,000 feet. It's this red spot here between the latitudes of -15 to +15 degrees, at least as exemplified by the Canadian computer climate model for this temperature trend. And the reason why there's this tropical hotspot is a bit involved, and I'm not going to go into the details associated with that here, except to say that it's a well-established prediction that everybody agrees on, that there will be this region of the atmosphere that is much warmer than at other latitudes of the planet and at other heights of the planet. And as a result, we can ask certain questions like, how do climate model predictions and retrodictions compare to observations for the global average temperature anomaly in the troposphere and also in the tropics? And by comparison, how do these predictions compare to ENSO warming models and their fit to observations of tropospheric warming over the tropics? And I say the tropics here because we've already seen that globally, ENSO warming models fit the data extremely well. So to address these questions, I want to first present a pair of charts from John Christy, one of which shows every CMIP-6 climate computer model, the latest batch of IPCC climate simulation models, and their predicted global or temperature trend in the tropics. These red bars represent the temperature trend estimates for 1979 to 2020 of every CMIP-6 climate model. And the black dashed line is the model average, which is plus 0.41 Celsius per decade. Whereas observations, which in this case refer to weather balloons, the average of 3 data sets, and something called reanalysis products, and the averages of those, is just 0.17 Celsius per decade. Not a single one of the CMIP-6 models matches the observational record. And we can see this in another way through this chart, which compares the predictions of the individual climate models with the observations represented by the dark green line corresponding to reanalysis product averages and the light green line corresponding to weather balloon averages. You can see that these two different observational data sets agree with each other extremely well, and they have relatively small variance, whereas each of these spaghetti lines representing an individual CMIP6 model has enormous variance, and the average of all of these model prediction trends deviates substantially from the observations. Now, this pair of charts doesn't have error bars associated with them or confidence intervals, and we would like to see such confidence intervals in order to be sure that these deviations are statistically significant and hence real deviations representing real problems with the models. So to illustrate that, this is a very compelling chart from a paper by Ross McKittrick and John Christy, comparing the trends, the global average temperature trends, or the temperature trends in the mid-troposphere globally, tropically, and also in the lower troposphere globally and tropically for each of the CMIP6 climate models. These are the red dots with the thin red error bars corresponding to 95% confidence intervals. And these are compared to the blue dots here representing the observational data with their confidence intervals. And as you can see, the average of all of the trend predictions for the models, this red dot here, or here, or here, or here, and the thick red confidence interval associated with that average deviates substantially in a statistically significant way. That is, the error bars do not overlap or only very, 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 very slightly overlap. In fact, if you averaged these observational data sets, the three of them, which correspond to the average of satellite data sets of UAH and RSS, also weather balloons, 3 data sets, and then reanalysis products, the error bars here would be even smaller and would safely exclude the model mean data and the error bars associated with them. So indeed, the CMIP6 models predict far too much warming on average than the observational data sets, which agree extremely well with each other. And this is a real disparity, not just a statistical fluke. So yeah, as I said, models with assumed net positive feedbacks from water vapor and clouds, such as the CMIP6 models, warm too fast globally and in the tropics compared to tropospheric observations by multiple data sets and multiple methods. And this implies that the negative feedbacks from water vapor and clouds must be significantly underestimated by models. As an illustration of this, it turns out that if one inputs to some degree an iris effect into the CMIP5 models via the so-called Enville cirrus clouds over the tropics, reducing in response to warming, then there is a significant reduction in the hotspot in the tropics. This was shown in an Elegant Nature paper by Morrison and Stevens, interestingly enough. So these models, of course, still have the problem of error associated with cloud coverage being far too great. Nonetheless, they do show that it can be shown that if you do assume something like an iris effect phenomenon, then that's going to reduce the hotspot prediction due to CO2 warming or other sources of warming. So now, how does ENSO modeling compare to the CO2, the CMIP6 or CMIP5 models for temperature variations in the tropics? So I want to return here to the paper by McLean and collaborators and show you this chart from their paper, comparing the derivatives of the Southern Oscillation Index, the black line, to the UAH tropospheric temperature anomalies, the gray line. And as you can see, the SOI 5 months earlier, the derivatives thereof, match extremely well in the tropics, the tropospheric temperature anomalies from the satellite data set. The only places where they deviate is where there were these significant volcanic events, El Chicon and Pinatubo. And in fact, they calculate that the variance in the temperature anomaly data set of UAH correlates to the SOI derivative by 5 months earlier by around 81%. So 81% of the monthly variance in the temperature anomaly data set in the tropics is accounted for by the Southern Oscillation Index 5 months earlier. So an extremely good fit to the data in this time interval. Not only that, but coming back to the work of Wallace and collaborators, we can look at how the average of UAH and RSS satellite data for the tropics, the temperature anomalies in the tropics, changes when one adjusts for changes in the multivariate ENSO index model that they considered. So here is the best fit line for that temperature data set, the blue line, the average of the two in the tropics. And when you adjust for changes in the MEI, the trend is completely flat. So that model, based on the multivariate ENSO index variables, fits the data there perfectly. It accounts for all of the warming in the tropical lower troposphere. Similarly, they show that for the average of 3 independent weather balloon data sets, the MEI-based model fit is excellent. And when you adjust for the changes in MEI, the trend is flat and non-significant once again. Now, in addition to their analysis of lower tropospheric temperature anomaly trends, Wallace, Christy, and DeLeo also show excellent fits between their MEI-based model and observations in the tropical upper troposphere, viz. Satellites and weather balloons. And further, they show an excellent fit with tropical Pacific temperatures via NINO buoy data, as well as excellent fit with tropical surface temperatures via NOAA surface station data. So in all cases, the MEI-based regression model fits the data extremely well. And a great virtue of this approach is that the MEI-based regression modeling is that it doesn't need to model feedbacks from water vapor and clouds. All of those feedbacks are already incorporated in the empirical data on which the model is already based. So it avoids a massive complication that, in my view, renders the climate computer models explanatorily and predictively useless, at least at the present time. So we've seen that ENSO warming excellently fits warming trends observed globally and in the tropics in the past half century, unlike the hypothesis of amplified CO2 warming, which is incorporated in these various computer climate models. And this has implications for the hypothesis of CO2 warming amplified by water vapor and clouds. It implies, first of all, that even amplified CO2 warming with a trend given by the satellite data, say 0.13 Celsius per decade, cannot be, because if we had that much warming on top of the warming due to ENSO, which also fits that data set extremely well, we would get far too much warming overall than observations show. And this implies that the net feedbacks from water vapor and clouds, as well as oceans and other aspects of the climate system, must be either zero or negative on CO2 warming. We can make that inference, that is. But now you might ask, well, what if CO2 warming significantly impacts the ENSO phenomenon? For example, maybe it causes slightly more and larger El Niños than La Niñas over time. Maybe that's already happened. Maybe it will happen in the future. So one thing we can say right off the bat is, as we saw, direct CO2 warming is far too small in magnitude to account for the multi-decadal shifts that we saw in the magnitude and frequency of El Niños and La Niñas. But you might wonder, what about amplified CO2 warming? Well, interestingly enough, CMIP6 models tend to predict a rise in sea surface temperatures, that is, and hence stronger El Niños in the 2 centuries, whereas CMIP5 models are ambiguous about this. There's no consensus in the CMIP5 models about whether El Niños would increase or not in magnitude or frequency. And the difference here is based on the greater positive feedback from water vapor and clouds that are assumed within the CMIP6 models. But the crucial point here is that since CMIP6 and CMIP5 models significantly overpredict warming in the troposphere, middle and lower troposphere globally, as well as in the tropics, their predictions for ENSO cannot be considered reliable. So we can safely infer, I would say, that the warming from ENSO and the warming from CO2, to whatever extent the latter is there, are effectively independent of one another, and that their total contributions are additive. The warming effects are effectively additive. So to wrap up the presentation, we've seen that the direct warming from CO2 alone is far too small to agree with observational data, whereas ENSO warming models fit observations globally and in the tropics extremely well, and in fact, vastly better than climate computer models that assume amplified CO2 warming. The latter models, in fact, predict too much warming relative to observations, which implies that they significantly underestimate the impact of negative feedbacks on CO2 warming, or the presence of negative feedbacks to CO2 warming. So ENSO warming plus CO2 warming with net zero or net negative feedback seems like a viable possibility compatible with observations, whereas amplified CO2 warming plus ENSO warming would poorly match observational data. So what we can infer from the previous points, namely that amplified CO2 warming plus ENSO warming poorly matches observations, is that CO2 warming must be playing a very minor role in global warming, and the net feedbacks to it can be inferred to be either zero or negative. I would like to do a future presentation for your podcast in which I expose some egregious deception from the group Yale Climate Connections as it relates to James Hansen's 1988 Senate testimony, congressional testimony, and his claim that his model predictions of scenario A, scenario B, scenario C correctly matched subsequent global warming observations.
So thank you very much for doing this. I know your first podcast here got high praise from Will Happer, so I really appreciate what you're doing. We'll talk to you next time.
Thank you. Appreciate it.